Ready for some shell action?
Oh yeah.
Okay, I brought in a great prop to illustrate the shell method. Roll of toilet paper. Okay. A little awkward walking in with this morning. But yeah, I need a softer ply here. All right, so the shell method is again going to take a volume. Now you can imagine that this, if you think about an axis running through the middle, and we're always going to make the axis running vertically, because again, AP doesn't need you to know this for their test, but it does make, in my opinion, doing vertical axes a little bit easier, because it eliminates the actual step of having to resolve like you did last night or yesterday in class for equations in terms of their y values. All right, so and most of the time you get problems, they are given as y equal in terms of x values. This allows you to not have to resolve. Basically eliminates a step that could possibly give you a careless error. All right, now you do have to understand a new method though. So I am going to test this on this test, but I'm not going to give you any problems beyond this test that would require a know the shell. So you can use it. AP accepts work that is done with shell method. They do that. So they're fine with it, but they don't give you problems that would require it in any way, shape, or form. And you can do the shell method for horizontal axes as well. I'm not even going to talk about those because, again, I'm trying to give you an alternative for vertical rotation. So I'm going to show it to you like this initially, but pretend there's an axis running through the middle, right? So that would be whatever the axis is, but now we're going to rotate it this way. So here's what the shell does. And if you read in my notes, this is kind of a proof of the shell, why it actually does what it does, but I don't think it's really necessary to understand that proof. So the idea is, if I were to just cut, I'm hoping I get a nice cut here. If I were to just cut right here, one layer, and again, I hope it's one layer. It's not the end of the world. But if I were to cut one layer off this shell right here, you can see that that one layer doesn't really affect the volume much, does it? But you obviously know that if I keep pulling layers off this, eventually there will be no more wipes. Are you with me? So clearly that this volume is a creation of a bunch of these shells. Are you with me? So I'm going to pull one of these off, and I want to think about what this is. This clearly has a little width, but not much width, right? So it's kind of like a very thin dx, because ours is going to be dx. So when I unwrap this, if I want to find the volume of this, I would need to go area of a rectangle, essentially, wouldn't I? So I'm taking the area of this rectangle and giving it a little bit of width. Now think about, how would I do area of this rectangle? It ends up the base, right, of this, the bottom of this, really was the circumference, wasn't it? Are you seeing that? So basically, I'm going the same thing at base times height, but to do base, I'm going circumference times this height. Are you seeing that? So basically what you're doing on all of these is circumference times height. Now, what is circumference? It's pi d or 2 pi r. We're going with 2 pi r, okay? Because we're going to be rotating about an axis, and that the distance from that axis to any point on this, which is going to be changing, but that axis right there is going to be that distance from, the radius is going to be that distance from the axis to the actual shell. Are you seeing that? And the great thing about this is, it's not like we're doing whole minus whole, where we got to go back and subtract the whole. When the layers are all gone, they're gone, right? The whole is empty space, but I don't give a crap because it's nothing there, right? You follow me? So it usually can be done with one integral. Now, there are times it takes two integrals, just like there are times when the disk washer method may take 3 or 4 integrals, depending on what the outer is, what's happening with this radius. Are you seeing that? Okay, so here's what we're going to be doing. This formula, you can scroll through most of this. It's kind of interesting. I actually read through. I hadn't read through it in years, but I was looking through that. I was like, oh yeah, I kind of forgotten that. But the bottom line is, and I'm going to keep scrolling down on this to this because some of these are very limited formulas, but I want you to see these. Okay, So essentially, what we're doing, again, is finding the area of this. But the area of this thing, if you put it back together, was formed by base times height. The base is the circumference, okay? So your base, which is, your base is the circumference, 2 pi times the radius, and then times the height, okay? Now your radius, just like before, my radius is going to be the distance from whatever function I have out here to the axis. But here's the thing. When you start thinking about these pictures, and I'll show you a few of them in a second, it always ends up being however far over you moved, which is your x movement, plus minus whatever the axis is. So when you go, like if the axis is over here, you're going to subtract the axis and you're going to get an x plus c. Or an x minus c. And if it was a negative value, you minus a negative. If the axis is over here, because you still like to go right minus left, you're going to go axis minus x. But it's the x value, that length, that you're adding or subtracting from. So literally, your base will always be x minus c or c minus x. It just depends on where that axis is. Okay? So when your axis is over here on the right, you're doing that. When your axis is over here on the left, you're doing that. Okay? Now, this f of x, in this particular problem it was f of x, it's not always, this is representing your height. Okay? But sometimes the height, like before, is not just the distance to the function. Sometimes there are two functions that you're rotating. So the height might be the difference between that f and g. But you'll see that in a second. So sometimes it's f, sometimes that height ends up being like f of x minus g of x, like this. But it's always going to have 2 pi on it, because 2 pi, sorry, what did I say base? The base is all of that. This is the radius. It's always going to be 2 pi radius times height, either f minus g, top minus bottom, because we're always going to be doing it on a vertical axis. All right? So I'm going to walk you through some of these pictures and help you see it. So take a look at this one. So I've got this shaded region. All right, I've got this shaded region, and it's bounded by the line y equals 0. So this bottom part is y equals 0. You could even call it g of x equals 0. And it's got a top function here that's y equals x to the negative 1/2. All right, and you could call that f of x, say, equals x to the negative 1/2. All right, now if I rotate this around, you can see it has this. And I'm fine to do disk and washers. If I want to make my slices perpendicular, you have a bunch of washers, don't you? But it would be a dy equation because you're stacking those washers up. But what we're going to do is peel off shells. So think about this as an odd roll of toilet paper, right? Be really uncomfortable on the front end, you know, a little bit better on the back, but an odd roll of toilet paper here. And my first shell is just going to be this very outer part. Okay, that's my first shell right here. Okay, but I think you can see that right here, if I were to slice it, say right there, and open it up, I get this big long ribbon, don't I? Right? And the height was just top minus bottom function. And it's going to continue to be top minus bottom, top minus bottom, top minus bottom, top minus bottom. So my height is not, in this case, it's f of x minus g of x, but it's just f of x because g of x is 0. But if there were a different function on the bottom, then it would be top minus bottom. That's your height. So your height part ends up being that f minus g. Okay? Now, then you go to the axis. All right? The axis over here, in this case, okay, the first one I did is say rotated about the y-axis. I'm going to talk about the axis x, this second one right here. So if I'm rotating it about the line x equals -3, then the radius, if you think about it, originally the radius was really big. And as I peeled off layers, it got smaller and smaller and smaller and smaller and smaller, right? Well, how do I find the length of this? Well, if you think about this as the y-axis right here, right, then any value on this, any distance, like if I'm going to right here, it's just the actual x movement. So that's why we always use x, because I'm always going out to that function wherever I am. But I also have this part that I need to add to it to make the radius. But again, if the axis is over here, you can just take that length, x, subtract that -3, and it basically says whatever the x movement is, add a 3 to it. And that's when the axis is over here. So that axis we call basically, that's the c value in the formula. And it's always vertical, so it's always a whole number. So if the axis is over here, I'm always going whatever the x value is minus the c. And if the axis is over here, I'm saying whatever the c value is minus the x to get the radius. And if you do it wrongly, guess what? If you accidentally go x minus c when it should be c minus x, guess what happens to your volume?
Negative.
It ends up being negative. And you see the negative there. Wednesday. All right. When you see that value negative, you go, oh yeah, I didn't get bailed out like I did on disc washer where I was always squaring it and it made it positive, so it never really mattered. But when you see the negative, you go back and you go, oh yeah, it wasn't x minus c, it was c minus x, or vice versa. So you bottom line, whatever that is, it'll be a -3. So I'm going to go x minus the -3 or x plus 3. That's going to go right in. That's going to go right in here. So this ends up being my radius. I tack on a 2 pi to make it circumference. I multiply that circumference, which is the base or the length, times the height. The height ended up being f minus g. But because the g was 0, all I saw was the f. Give it a little width, and you integrate again from what? And here's the great part. I integrate not from -3 to 4. I'm back to just using that interval from 1 to 4 right there. So from 1 to 4, and then you knock it out. All right? Is that making sense so far? All right, so again, this is an alternative for you on vertical axes. If you're like, oh man, I forgot how to solve for that logarithm. How do I resolve for x in terms of y? I forgot my log and my exponential rules. Well, you don't have to work, because some of you actually did a great job on that problem. I mean, you made it harder for you, I thought, but on the last test, you did a great job converting from e to ln or ln to e. You did, but a couple of you didn't. A couple of you butchered that, and it cost you 4 or 5 points on that problem. So this would have been an example where if you felt the need to resolve on a volume of rotation, you could go, wait, I got another method for vertical axes. I don't have to do it. I can keep it all in dx. All right? So let me see if I can find another better picture. It works well. None of these problems are wonderful. I don't know why I still have them in here. How about we just make one? Okay, we're going to change number 1. I think I have these nice diagrams and I like to use them, but they're kind of baby problems, so they don't stretch you. So we're going to make this 1a, and we're going to say, all right, the top equation is y equals x minus x cubed, and we're going to add a bottom equation right here, and that equation is going to be y equals x squared minus x. Okay? So top equation, bottom equation. And we're going to rotate this right here. So here's my new shaded region right there. It's all of this shaded region right here. We're going to rotate this about the line x equals 2. So when I rotate it, I get this odd little donut looking thing. And of course, if I want to, I could actually do slices all day long. But to do that, slices, I'm going to have to solve these, right, in terms of x equals y. And I don't have the math to do that. So this is where this really becomes helpful. I can't solve it that way and do disc washing now. AP won't give you one like that. They won't force your hand. But I might on this test just to see. So right here, because it's hard for me to solve those for x, I mean, there might be some algebra out there that we just don't know yet. What we're going to do is rotate it like we did. We're going to rotate it around, and we're going to do disc washer. So what I'm going to do is start peeling off outer rolls. Now, again, I don't have a roll of toilet paper that looks like that, but imagine again, the first, when I pull that off, I need to know 2 pi r, right, for the length, right? And then I need to know height. So how would I calculate the 2 pi radius part, and how would I calculate the height part? So for that right there, for the length, which is 2 pi radius, I've got the 2 pi. How do I find the length of the radius? Now, if you just use your formula, what is it? The radius, if the axis is over here, c minus x. And your c is 2. So if you just want to brainlessly use the formula, you can, but I will show you why it is. So all I really have to do is go, the radius was the axis was 2, x equals 2, that's your c. So 2 minus whatever x value we're talking about. Now again, this is why this works. If I were to rotate this, okay, and let's just say, I'm going to get rid of that so you can see this a little better. Okay, let's just say I'm peeling off this shell right here. So again, I'm rotating this around. So there's this really big shell over here. Okay. Terrible looking shell, but whatever. I think you get the idea, right? So I'm going to need to know from here, what is the radius from here, right there, all the way to that? Well, it's not 2, right? Because I'm not counting that little part. So what is the x coordinate of that? Well, I don't know because it's changing. It might be there. It might have been there. It could have been all kinds of different places. But that little length right there is an x length, isn't it? It's a length of x. So I'm taking the whole 2 and subtracting off that x. So when x is 0, it's 2. When x is 0.5, it's 1.5. Because it's always 2 minus that x length. But you don't have to overly think about it. Axis on the right, 2 minus x. Axis on the left, x minus 2. Every time. Are you tracking with me? So here we go, 2 minus x. And then I'm going to go over there and go, what's the height? How do I find the heights of each of these right here? How do I find any height measured right here, no matter which particular thing I'm using? What is the height? Top minus bottom. And if it's labeled f of x and g of x, you're welcome to do that. In this case, it's not. So top, x minus x cubed, minus bottom, parentheses, x squared minus x. So 2 pi radius times height. That's the area of my ribbon? Yes.
Why is the x in the radius, like where is that x coming from?
Remember we said that little length right there is x. This length from 0 to here is 2. So if I go 2 minus that x value, that leaves me what's left over.
Oh, I thought that was.
And that's your radius.
Is
and
that line meet before the?
Is that what?
Does that line meet before the y-axis?
What line?
Like the x. Is that not at 0?
It's in all kinds of places. As I peel off layers, what happens? This gets big. Think about this as a giant roll of donut-shaped toilet paper, right? As I'm peeling off the layer, the first layer is literally 0. The first outside, it's so close to 0, right? You peel it off, it's like a string. But as I peel off more layers, the height gets bigger and bigger and bigger, and the radius gets smaller and smaller and smaller. So as x is 0, then yes, the radius is 2. As x is 0.1, now the radius is 1.9. As x is 0.5, now the radius is 1.5. When x hits 1, the radius is 1. And it's never going to go past 1 because I'm going to limit it from 0 to 1. So once it hits 1, you just got open space here. There's nothing to calculate. But this lets the x range from 0 to 1, which means the radius is going to range from 2 to 1, right? Radius is 2 here. It's 1 there. And then the heights are always the product of those, well, not the products, but they're always a result of the differences in the top minus bottom, right? They change from very little to nothing to maybe closer to like 1 and then back to 0. Are you seeing this? And then, of course, 2 pi r is length times height. Give it a little width. What, 0, 1. Are y'all with me? Okay, let's try it a different way. What if, you'll see it's just the same kind of thing over and over. What if I made the axis over here at, let's just say 1/2. So this is, negative 1/2. X equals negative 1/2. Right? And again, I'm going to use the line y equals x squared minus x. Right? So when I rotate it now, I get a donut going this way. But what do I need? If I'm going to do the shell method and peel off shells, I need to go 2 pi times the radius times the height. That's going to give me area. And then I'm going to dx it to give me volume. And then I'm going to integrate from, again, 0 to 1. Now let's think about that. You want to just memorize? Axis is on the left. What's the radius? X minus c. Like, you don't have to overly think about this. It's going to be x minus c. And because your c is negative 1/2, x minus a negative 1/2 is what? X plus 1/2. Now let's think about that. For any point on this graph where you're like, say this is your first ribbon, right? your first one's way over here. Let's just start with that. Okay. So when I first peel it off, I've got this really, I'll do it in a different color. I've got this really small, thin, smaller than this actually. I'm just trying to illustrate something. Whatever. Terrible. Y'all with me? Very thin little rolled piece of toilet paper. I need to know this radius. Well, the radius from the axis out to here, this is 1. This is 1/2. It should be 1.5, right? So on one of the x values, when it's 1, radius is 1.5, right? Now, as this gets closer and closer in here, now I might have that as a height. So now my ribbon, or my shell, I'll call it ribbon, my shell might look something like this. It might be much taller. Right? Now what's my radius? Now my radius is still that distance. Well, that is a unit of x. It's always a unit of x. But you have to add to it a 1/2 length, x plus 1/2. And you don't even have to think about it, guys, really. But that's the math of it. You're taking whatever that movement was on the x, adding or subtracting whatever it is from the actual axis to get that extra value. And if the axis is right on the edge, well, then you're adding or subtracting nothing, because it would be x equals 0, right? And then you just do the height. What's the height again? Top minus the bottom. So 2 pi r, that's the length of the toilet paper, times the height, that's the area of the toilet paper. Get a little width and integrate only where the x values matter, which are from 0 to 1. So you don't go from -3 to 1, because what that'll do, remember, this graph keeps going, right? This graph right here does something like this, goes down and back up, and this graph keeps heading up. It's going to take that area and find it, except it's going to calculate it as that volume, it's going to calculate it as negative, because now the heights have switched, the top and the bottom have switched. It's going to mess up your volume if you go from 0 to 1. If you go from -1/2 to 1. So you always go from where the region occurs, which is 0 to 1, and then you don't get that extra jump in there. You seeing it? Go show. All right, what about this? We're going to we're ugly this one up too. So number 2A. So same problem, but we're going to add to this. So here's our region. We're going to add to this y equals x equation. we're going to add to it y equals x squared minus 2x. Okay, so it gives us all of this region, and we're going to rotate this about this axis, which is the x equal 3 axis. So we're taking this region. So to do that, we might have to change. It says revolving the plane region. I guess it was shaded better on my before I printed it, but we're going to use this region right here. So what do? I'm not going to keep preaching everything. Let's just get after it. What do? So 2 pi. I'll omit the integral for now. What's the radius? 3 minus x. Don't even have to think about it. What's the height? Top minus bottom. So x minus the x squared minus 2x, or you can write x minus x squared plus 2x, or you can write x squared plus 3x, because that's what it simplifies to, which is probably what you would see on a multiple choice question. Base times height, or length times height. Give it a little width, and integrate from 32. And if I had to actually do the math on this manually, which is very likely, okay, to me it's a little bit easier a lot of times because you don't always have the, I mean, you might have the pi or the 1/2, all the other stuff that you have. But right here, all I got to do is take this 3 minus x. This is really x minus x squared plus 2x, or 3x minus x squared. And what would you do to integrate that? I'd FOIL it out, because if I call that u, I'm going to end up with 3 minus 2x, and I don't have a 3 minus 2x. It's close, but I have a 3 minus x. So doing a u substitution is not going to work great for me here, but I could certainly FOIL it and get 9x minus 3x squared minus another 3x squared plus an x cubed. And those two negative 3x squareds become a negative 6x squared. And that shouldn't be that hard to integrate. So I get 9x squared over 2 minus 6x cubed over 3, which is 2x cubed, plus x to the 4th over 4. All of that times a 2 pi from 0 to 2. And when you plug the 0 in, it's giving you nothing. But of course, you plug in the 2 first. You just plug in the 2 and simplify, and you're on your way. You with me? I hope this is helpful. Like, again, I'm going to test you on this test, and after that, it's just your call. And there are times when the shell method will make your life harder. And honestly, because the shell method might require, like if, for instance, what if I gave you a region like this? Right, so it's made, say, of a function right here, f of x, and a function right here, g of x, and a function right here, h of x. And you rotate it about this. Are you seeing that? So for me to do this, I'm going to have to do what? I'm going to have to calculate the radius. That's easy, right? X minus c, x plus c, whatever. In this case, c minus the x. But then I got to do the height. But what happens on the height? It changes because the top changes, doesn't it? So in that case, I would have to have 2 integrals. But at least I wouldn't have to resolve everything in terms of y. If I did disk washer on this, what am I doing? What hole minus hole? Outer radius, same function. Inner radius, same function. Well, I might have to change, but I can still do it in 2 integrals. So it doesn't, sometimes it's not overly helpful. Sometimes, but you know, hopefully at some point you're going to be pretty adept at this, and you'll look at it and maybe go, all right, vertical axis, I got a couple options. What seems easier to me? And especially if I gave you the equations x equal in terms of y, well, why not? It's already x equals. And a lot of times AP will give you x in terms of y, and you can't solve for y. The math would be too hard. Like, what if I told you that this was x equals y cubed minus y? If that was this graph right here. And right here, I I told you that was the line y equals 2. I told you this was y equals 1. And I told you this was x equal, I don't know, 3. And then I told you this right here is x equal 4. So I don't know, whatever. You've got the x-axis coming in somewhere. If you're rotating this right here, for me to do disk washer, I have to solve for y. I can't do that. I don't have the math to solve x equals y cubed minus y in terms of y. I can't. And by the way, you can't go, yeah, you can. It's y equals y cubed minus x. You can't define y. Somebody did that. Actually, they defined x in terms of y and x. You can't do it. You got to have one x on the right, all the y's on the left, no other x's. Leaving an x in terms of, in the definition is like defining beauty in terms of beautiful. You can't reuse the actual word in the definition, you know. You've got to come up with something more different and creative. Same thing here. So a situation like this, I would be forcing your hand on using disk washer. But again, if I'm not forcing your hand, you have that as an option. All right, what about this one? This one I don't have to change much to make it interesting. Yeah.
If you're going to ask us to manually solve, do you want us to turn pi to 3.14 to do this pi?
Definitely not. Leave pi as pi. Yeah, don't ever do that. If it's a calculator problem, then you don't even have to bother. You can just type this in, right? So don't do that. But and also remember, if it's free response doesn't technically make you simplify. People are really starting to see that. So technically on free response, you could plug that in and say, I mean, this is me simplifying a little bit, but I'm saying, all right, 18 minus 16 plus 4 minus 2 pi 0. I could leave it like that on a free response. I technically could just plug the 2 in and go 9 times 2 squared over 2 minus 2 times 2 cubed. I mean, free response doesn't care about the simplifying like you would think. It almost is to the point of being uncomfortable. So what I do is if it's brainless stuff, like 2 squared is 4, that cancels with the 2, I can multiply by 9. To me, that's brain. 2 cubed is 8 times 2 is 16. 2 to the 4th is 16, divided by 4 is 4. I can do that stuff. But when it comes, and even this right here, to me, that's not a big deal to say 12 pi here. So I'd probably do it. But if it ever gets to where you're like having weird fractions and you start to get a little uncomfortable, on a free response question, you can leave it unsimplified and you're okay. Just remember that. But on multiple choice, obviously, your answers have to match the multiple choice did. All right, check out this one. So what if I rotated about the axis x equal 4? So that's not drawn in there, but it's over here. Real quick, help me out. What do? 2 pi what? 4 minus x. Guys, I'm just really, don't overthink that radius. I mean, I overthink it for today to explain it, actually why it is what it is. But after that, man, it's just 4 minus x or x minus 4, depending on where the axis is. And the height? What's this? That's y equals 8. And what's this? That. So top function, which is 8, minus bottom function, which is x squared plus 4. Make sure you put that in parentheses. Y'all did a pretty good job of that. I think there's one person who kept forgetting to put that second parentheses in there. Out of the class of 30-something. So that's pretty good. Most of you are really good with that. So that's base times height as your area. Give it a little width. That's your volume. Integrate from what? I think it's 0 to 2. Have you checked it? If I set y equals 8 and that equal to each other, right? I get x squared equals 4, so plus or minus 2, but we're at positive 2, right? So definitely 0 to 2. But always check those out because it might not be. It might be square root of 5 when you do the math on it, right? If that's x squared plus 3, it would look very similar to this, right? Very, very similar, except it would be coming right in here. And it would look like it was at 2, but it wouldn't be. It would be at root 5, which is like 2 points. So be careful about that. Don't ever assume. The word, not many of you did, which is really great. A couple of you assumed that one of those values in the test was 1, and it was really like 0.96 something. So really, y'all are much better off. I mean, as a class, leagues beyond my other classes in your understanding and ability to process. And I'm revisiting how I'm going to do this review. I think I'm going to give you one of my former tests, which is on big theorems, rules, all that stuff to kind of jog your brain. Because like right now, if I were to say, all right, life or death, write the mean value theorem up here. That's what I mean. It's not hard. And some of you might be like, wait, I remember that. But a lot of you are like, what? It's like, whatever. So I'm going to go through that, like relationships between F prime, F double prime, little charts I gave you. We're going to do 1 4 or 5 day jaunt through that, maybe even 4. And I'm going to give you all these theorems. You're going to start memorizing them, reminding yourself of it. We're going to have one theorems test. And then I think we're going to abandon what I've done in the past. And I'm going to start giving you practice test after practice test. And if I can get 4 in, I'm probably going to keep your best 2. Or no, unless they start going downhill or whatever. So I might keep your last 2. Or maybe if you're all good, I'll keep your all 4. But whatever it is, I'm going to look at this and find a way to see if we can hit a crescendo at the end. And then the very last one, like maybe the first one I give you will be practice. So I'll send it home. Like I'll send a little one section of the test home, which is like 45, 55 minutes, which early on doesn't take you 45, 55 minutes for the most part because you don't remember stuff, but a lot of the times. So, but as you get through it, it'll be more accurate. And at the very end, I'll just give you the whole test in class, maybe 8 days before the test. And we'll take it over 4 days. And then 3 days, the next 3 or 4 days, we'll review it. And sadly, a lot of this stuff I can't let leave my classroom. So I won't be able to go. I mean, there's a couple I could send home because they've been released. But a lot of these haven't been released. So I have to keep them in here. And but we'll do that and we'll just accumulate grades that way. And that way, I think we might be able to get 4 full-length practice tests in here. And if we can do that, you guys are going to be in great shape, I think, if you pay attention and hang in there to the last little bit. I know that's hard. You see the end finish line right now. I mean, y'all are 2 months and 2 months and 2 days till you're done here, at least in this building. I mean, you might come back for an AP test, but it's March 3rd, man. Your last day is May 7th. Well, 4 days, 2 months and 4 days. It's right there. So it's like running a marathon and bailing in the last mile. Don't do that. That's foolish. It's one thing to come up lame. I had a friend do that, actually. He's the older guy, he's 47, but he's still crazy shape, and he runs half marathons and marathons. And he was breaking his all-time PR in his half marathon at the age of 47. And he ran track at Gustavia and stuff like that. Really good athlete. But he's in crazy shape. And he got literally a half mile out, tore his calf muscle. And then he tried bouncing on foot. And he's like, I can't go a half mile on one leg because his other leg started cramping. And then he tried limping for a little bit. Anyway, needless to say, he didn't get his PR, but he still tried to finish strong. For you guys, we're going to hit a crescendo. The more we do these tests, the better you're going to be. The more you're going to go, oh yeah. And you're going to fill in these gaps. But I'll give you all the theorems first. And you can kind of hopefully dig up some of that stuff, give you some tools. It's like some of you don't remember all your integral rules. I mean, I don't. I forget them too. Like, oh, what's the integral of the natural log of the bubble? Or not, well, we'll do those. What's the integral of, the ugly ones, and the inverse trig ones and all that kind of stuff? You forget that stuff. Now, the upside is I'm not going to test you on all of it. I put little asterisks. I'm giving you these notes because they're a great resource for the future, like if you need to brush up on stuff. But I'll put an asterisk by stuff that you don't need to know. Like some of them, I'm like, I've never remembered an AP problem covering this, and I've taken 20 AP tests. Skip, don't bother. It's not worth the brain cells. But some of them are great, and you're going to need to know all that stuff. So I just printed it off. It's not a short packet or small packet. But. All right. Any questions? So process this. Today is Wednesday, right? Our test is next week on Wednesday. No, Wednesday? So we're going to do classwork tomorrow, guys. We're going to do more area and curves and volume on Friday, and I'm going to give you a take-home quiz. I would advise you to do it. And then on Monday, we're going to go over the take-home quiz, do a few extra problems. You won't even be in here on Tuesday because the juniors are taking the ACT. And then when you come in here on Wednesday. So we're gonna have a 3-day review on this. And I'm not teaching anything else new. So if you don't do well on this test, dude, look in the mirror. That's who you need to be angry at. Because I really shouldn't be giving you this long. I really shouldn't. It's, I should be making better use of this time. I want everybody to finish strong in this 9 weeks. All right?
I will not be here Thursday or Friday.
Next week?
Today or
This week?
tomorrow, yes. Can I go ahead and get that practice